Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at multi-stage events. That is, we're going to find the probability of an event that occurs in stages. So to do that, we're going to look at independent events in a second. But first, I want to give you an example of a multi-stage event. So here we have a coin tossed and a die being rolled. So this event occurs in two stages. Stage one, the coin. Stage two, the die. So we're going to calculate these probabilities. So one way that you can calculate probabilities of multi-stage events is to list all of the outcomes in either a table or a tree diagram, and I'll show you the tree diagram later. But let's use a table to list all possible outcomes when a coin is tossed and a die is rolled. So for the die, you can get 1, 2, 3, 4, 5, 6. And of course, from the coin, you can get heads or tails. So we fill in the table like this. So you can get heads on the coin and 1 on the die, heads on the coin, 2 on the die, tails on the coin, 1 on the die, and so on. So here I've listed all of the outcomes of which there are 12. So each of these 12 outcomes is equally likely. So the probability that heads is tossed and a 4 is rolled, well, let's just find which one satisfies that. It's just that one. There's one way that can occur out of 12 outcomes in total. What about the probability heads is tossed or a 4 is rolled? So in order to calculate that, we have to include all of the ones in which heads is tossed and any in which 4 is rolled. So we can see that there are 7 such outcomes out of 12 in total. So probability 7 over 12. So that was all well and good for this. This is quite an easy example, but you can probably guess that there will be times where the total number of outcomes is so great it would be impractical to draw a table like this. What's more, it would become more complicated if each of these outcomes was not equally likely. So, although drawing up a table is good for some easy questions, let's come up with another method to solve this here, and that involves independent events. So two events are said to be independent if they don't affect each other. In other words, one event does not change the probability of the other. So if you have two events that are independent, you can use this formula. Probability A and B equals probability A times probability of B. This says if you have two independent events, the probability they both occur is just the product of their respective probabilities. So in this example here, the outcome of the coin and outcome of a die are independent. One doesn't affect the other. Doesn't matter whether you get heads or tails on the coin, it won't change the chances that you get a 1, a 2, or a 3 on the die. They don't change each other's probability at all. So we could let A be the event that I toss a head and B the event that I roll a 4. The probability that both occur, that I toss heads and roll a 4, is just the probability of heads. So the probability of heads is a half times the probability of rolling a 4. Probability of rolling a 4 is 1 over 6, and I get 1 over 12. Note I got the same answer here. Now let's calculate the probability that I get A or B, that I toss a head or roll a 4. So we learned in a previous lesson the OR rule for probability is its probability of A or B equals probability of A plus probability of B minus probability of both. And the probability both occurred, we just calculated. And it turns out we get the same answer, 7 over 12. So when you get a multi-stage event like this, you can draw a table or a tree diagram that I'll show you later to list all the possible outcomes. That works for the easy questions. However, that won't always work for the more complicated questions, particularly if there are heaps of different outcomes or the outcomes are not equally likely. In those cases, this formula is very, very useful. All right, as promised, I'll now show you a tree diagram. So a family has 3 kids. Each time there's a 50-50 chance it is a boy or a girl. We're going to calculate the probability to have 3 boys or 3 girls. So I'll show you this example using a tree diagram and then formula. So here's how you draw a tree diagram. Once again, it's for multi-stage events. So each stage is a column. This event occurs in 3 stages because you're having 3 kids. And each time you have a kid, there are multiple possibilities. You can have boy or girl, and then the second one, you can have boy or girl. So it's called a tree diagram because it branches off like this. Now, if you get a boy second go round, you can still have boy or girl third go round. The whole point of tables and tree diagrams is simply to list all of the possible outcomes. So to find the possible outcomes, we just go across the branches. So the first possible outcome here is B, B, B. We also have boy, boy, girl. And we keep going in this way until we've listed all the outcomes. So here we've listed all outcomes. Now it turns out each of these is equally likely because we said 50-50 chance at each stage that it's a boy or girl. So what's the probability there are 3 boys or 3 girls? Well, we just go to our list of outcomes and we find the ones that have 3 boys or 3 girls. We can see the required probability is 2/8 or 1/4. So we've solved this using a tree diagram, but we could also use independent events. See, the point is if the probability of it being a boy doesn't change each time, then they're independent. It doesn't matter what the first child was, it's still 50-50 boy, girl on the second child. That means they're independent. So that means the probability of getting boy, boy, boy is just a half times a half times a half cubed is 1/8. It also means the probability of getting girl, girl, girl is a half times a half times a half, which is 1/8. So the probability of this or this, remember, and basically means you times, or means you add. So the probability of either of these is just these two added. So these two are mutually exclusive. You can't have 3 boys and 3 girls if you only have 3 kids. So the required probability is 1/8 plus 1/8. I got the same answer either time. So tree diagrams are easy to use, but they take a while. This one's a little harder because you had to realize that 3 boys or 3 girls includes both of these outcomes. Sometimes people forget one. So either method you use is fine. All right, let's look at one more example. So I travel through 3 traffic lights on my way to work. Probability first light is green is 0.8. If a light is green, the probability that the next light is also green is 0.8. If a light is red, probability the next light is green is 0.5. We're going to calculate the probability that exactly 2 lights are green. So this is a tough question, but first note, we're traveling 3 traffic lights. So there are 3 events. There are 3 times where there are multiple possible outcomes. Either the light is green or the light is red. So we can turn this into a tree diagram. So the first light can either be green or red, then the next one can be green or red, and so on for 3 lights. So really the only point of a tree diagram or table is to list the possible outcomes. So let's go ahead and do that. So first one is green, green, green. Then we have green, green, red, and so on. Now, in the previous example, each of these was equally likely, but that's not the case here, because at each stage, green and red are not necessarily equally likely. In that case, what we're going to do is we're going to write the probabilities on the branches. So for the first light, probability of green is 0.8, so the probability not green is 0.2. So if you get a green light, the probability the next light is green is 0.8, which means probability not green is 0.2. If you get a red light, the probability the next light is green is 0.5, and so on like that. Here we have a green light, so probability the next one's green is 0.8 and 0.2. Here we have a red light, so the probability the next one's green is 0.8, 0.2. All right, now we have to go and highlight which of the outcomes in which we're interested. So we want the probability that exactly 2 lights are green. So let's go and highlight the ones that have exactly 2 green lights. We've got this one, and this one. So we're only going to calculate the probabilities of these 3. So how do you calculate the probabilities? Well, you just multiply the branches. So for green, green, red, it's 0.8 times 0.8 times 0.2. So of course you can use your calculator for that. We get 0.128. So for green, red, green, we go 0.8 times 0.2 times 0.5, which is 0.08. And for the last one, red, green, green, we multiply 0.2 by 0.5 by 0.8, which is also 0.08. So remember that each of these is mutually exclusive. If you pass through 3 lights, you can't get green, green, red, and green, red, green. So when you have mutually exclusive events, the probability that any of them happen is just the sum of their respective probabilities. The probability that this or this or this happens, I simply add up these 2 here, and I get 0.288. So the tree diagram may help give a visual understanding of what's going on and listing all the outcomes, but we could have completed this question without it. So it is a bit difficult to do this question without a tree diagram because you have to realize that there are 3 ways the event can occur. Green, green, red, green, red, green, or red, green, green. That's the hard part of doing this question without a tree diagram, is realizing these are the ways the event could occur. But once you've realized that these are the ways the event can occur, you can just use what we learned about independent events. We just multiply their probabilities together. And that's essentially what I did over here. So 0.8 times 0.8 times 0.2 and so on. So whether you want to use a tree diagram or table or independent events, just use the formula, is up to you. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.